In this video, we're going to talk about the concept of chirality. One of the most perfect examples of chirality are your hands. Hands are non-superimposable mirror images, meaning that they are mirror images of each other, but you can't put one on top of the other. If you replaced your left hand with a right hand, this wouldn't work out very well. That's what we mean when we say that hands are non-superimposable mirror images. The term chirality then means that something has asymmetry. A chiral object is not the same as its mirror image. If we look on the left here, you can see that a corkscrew that goes clockwise is a mirror image of one that goes counterclockwise, but they are not identical. Same thing if we look at the shell here. You can see that this side of the shell is a mirror image, but not identical to this side of the shell. If we apply the concept of chirality to molecules, chiral molecules then have an enantiomer. A molecule that is achiral does not have an enantiomer. Let's look at an example of a chiral molecule. One example of a chiral molecule is ibuprofen. Ibuprofen is the active ingredient found in a lot of pain relievers. For example, Motrin and aspirin contain ibuprofen. You can see a picture of generic ibuprofen over here on the right. Ibuprofen typically comes in two forms, the active form and the inactive form shown here. You can see that the active form of ibuprofen is chiral because it has an enantiomer. Because your body is chiral, it only recognizes this form of ibuprofen. So about half of the ibuprofen you're taking really isn't very effective. Your body can convert the inactive form to the active form, but the process is slow, so it's probably not very significant. To test for chirality, you can do what's called the plane of symmetry test. If the left side of the molecule is the same as the right side, then we have an achiral molecule because we have a plane of symmetry. In the example here, you can see that the left side of this molecule is the same as the right side. This view is from the top, and again, the left side is the same as the right side. So this molecule over here on the left has a plane of symmetry, so that makes it achiral. The molecule on the right does not have a plane of symmetry. You can see that the left side over here is different from the right side. This is very clear in the top view as well. The left side is different from the right side. This molecule does not have a plane of symmetry, so this molecule is chiral. Let's use this model to look at an example of an achiral molecule. An achiral molecule will have a plane of symmetry. When we look at this molecule the way it's drawn, it's not very obvious that there's a plane of symmetry. It looks like the left side is different from the right side. So let's do a rotation. And now hopefully you can start to see that plane of symmetry. If we cut the plane of symmetry down the middle here, you can see that one side is the same as the other. So the plane of symmetry isn't always obvious. We oftentimes have to rotate the molecule to see if it has a plane of symmetry. Now if we change one of these hydrogens to a different atom, now it's very clear that we no longer have that plane of symmetry. We can rotate the molecule all the way around, and we do not have a plane of symmetry. This molecule has what we call an asymmetric center. This carbon is asymmetric because the four atoms attached, or the four groups that are attached to it, are all different. So this carbon is considered to be asymmetric. We also consider the molecule to be chiral because it does not have a plane of symmetry. We'll talk more about how to identify asymmetric centers in the next video.